US Physics Olympiad year 2011 USAPHO Semifinal exam. This exam consists of 2 days, each day for 60 minutes. First day there were 4 problems, which was part A, and the second day was 2 problems, part B. Problem A1. Solutions for all problems you can find below this video in the reference of the description. Single bubble sonoluminescence occurs when sound waves cause a bubble suspended in a fluid to collapse so that the gas trapped inside increases in temperature enough to emit light. The bulb actually undergoes a series of expansions and collapses caused by the sound wave pressure vibrations. We now consider a simplified model of a bubble undergoing sonoluminescence. Assume the bubble is originally at atmospheric pressure E0 equal 101 kilopascal. When the pressure in the fluid surrounding the bubble is decreased, the bubble expands isothermally to a radius of 36 microns. When the pressure increases again, the bubble collapses to a radius of 4.5 microns, so quickly that no heat can escape. Between the collapse and the subsequent expansion, the bubble undergoes isochoric constant volume cooling back to its original pressure and temperature. For a bubble containing a monatomic gas suspended in water of temperature T equal 293 Kelvin, find A. The number of moles of gas in the bubble, B. The pressure after the expansion, C. The pressure after collapse, D. The temperature after the collapse, and E. The total work done on the bubble during the whole process. You may find the following useful. The specific heat capacity at constant volume is CV equal 3/2R. The ratio of specific heat at constant pressure to constant volume is gamma equal 5/3 for a monatomic gas. Solution. To start solving this problem, first let's draw the VP diagram for this process. Initially we have point 0 with a initial unknown volume, but in point 1 we have a known volume which has a radius 36 micrometers, and that was isothermal expansion. After that it was adiabatic compression, and because this process is adiabatic, it means that this curve increasing much faster, so it reaches point 2, which is higher than point 0. That's new pressure with the same volume as in point 0, and that was volume with the radius 4.5. So we know what is volume in point 0, we know what is temperature in point 0, and we know what is pressure in point 0. From this data we can find what is number of moles in this bubble. For that we use ideal gas law. This is our equation. Now we can find what is number of moles. That will be in point 0 pressure multiplied by volume divided by R, and temperature T. So when we put numbers, we will get 1.58 multiplied by 10 power negative 14 moles. That was answer for question A. Question B. Find the pressure after the expansion. It means that in point 1, here we have isothermal expansion. So we have this isothermal equation. P0 V0 equal P1 V1. So from here we can find what is P1, pressure in point 1. So P1 equal P0 V0 over V1. After when we put numbers, we will get 197 pascals. So that's the answer for question B. Next question is C. The pressure after collapse in point 2. So here we have adiabatic compression. We have this formula for adiabatic compression. So from here we can find what is pressure in point 2. So using this adiabatic formula for adiabatic compression, we can find what is pressure P2. That will be 6.46 at 10 power 6 pascals. That was answer for question C. Question D. We need to find the temperature after collapse in point 2. So here we have same volume, and in point 2 and point 0, and we know what is temperature in point 0. So we have pressure proportional to temperature. So temperature will be T0 multiplied by P2 over P0, which is these numbers. So that will be 1.88 by 10 power 4 Kelvin. So that was the answer for question D. And the last question E. The total work done on the bubble during the whole process. So during isothermal expansion, gas doing positive work from point 0 to point 1. It means that on gas there is negative work, which we mentioned by sign negative. And this is the expression for isothermal process. So that will be just a logarithm of this relation between V1 and V0, and finally we can put numbers and get this result for work done on gas in process from 0 to 1. Next process is adiabatic compression, and during adiabatic compression the total heat is 0. It means that all work done by gas, it's going because of change of internal energy, and we just need to find what is a change of internal energy for gas from point 1 to point 2. So total change of internal energy equal N multiplied by CV, now delta T, where delta T is T2 minus T1. Finally, that will be 3.64 times 10 negative 9 joules. And total work on gas, so that will be answer for question E. W1 plus W2, which is equal 3.40 10 power negative 9 joules. US Physics Olympiad, year 2011, USAPHO, semifinal exam. Problem number A2. Solution for this problem you can find below this video in the reference of the description. A thin uniform rod of length L and mass M equal 0.258 kilograms is suspended from a point a distance r away from its center of mass. When the end of the rod is displaced slightly and released, it executes a simple harmonic oscillation. The period t of the oscillation is timed using an electronic timer. The following data is recorded for the period as a function of r. What is the local value of g? Do not assume it is the canonical value of 9.8 meters per second square. What is the length L of the rod? No estimation of error in either value is required. The moment of inertia of a rod about its center of mass is 1/12 mL square. You must show your work to obtain full credit. If you use graphical techniques, then you must plot the graph. If you use linear regression techniques, then you must show all of the formula and the associated working used to obtain your results. These are experimental data here. Solution. We can use a formula for a period of a physical pendulum. This one. Period equal to pi multiplied by square root from moment of inertia divided by mgr. Moment of inertia for physical pendulum using parallel axis theorem equal this expression. Now we can insert this expression to this formula and find expression for the period. Now look at this formula. Here we have to find what is a g and what is L. And we have experimental data for period t and distance r. So we can linearize this formula in form of this expression. If you look carefully to this formula, we have data for r square, we have data for this coefficient to g, and we can represent this formula as a graph like this. Here we have y must be equal r square, x equal this expression, and b equal this expression. So now we can draw the graph for this formula. First we can do table. Using this experimental data we can fill this table with the coefficients, and after that draw the graph. Graph will look like this, and from this graph we can find what is the slope of this straight line and what is the coefficient b which crossing this line. So finally we can find that this g equal 9.179 meters per second square and L equal 1.47 meters. So that's the result. US Physics Olympiad year 2011 USAPHO Semifinal exam. Problem A3. Solution for this problem you can find below this video in the description reference. A light bulb has a solid cylindrical filament of length L and radius A and consume power P. You are to design a new light bulb using a cylindrical filament of the same material operating at the same voltage but emitting the same spectrum of light, which will consume a power Np. What are the length and radius of the new filament? assume that the temperature of the filament is approximately uniform across its cross-section. The filament doesn't emit light from the ends, and energy loss due to convection is minimal. Solution. First, let's write equation for power according to geometry. If we use the same material with the same temperature, power must be proportional to side area S, which is equal to 2 pi AL. So it means that power must be proportional to A multiplied by L. So that's the emitting power. And from other hand, that must be equal to producing power. And producing power we can count from formula V square over R. Now let's count what is resistance of a new bulb compared to geometry. So resistance equal to resistivity multiplied by length of a bulb and divided by cross-section area, which is pi a square. So connecting this power and this resistance, we will find that power must be proportional to a square over L, because voltage and resistivity is the same. And now we can combine these two powers, because emitting power must be equal to produced power. In other case, we will get destroying of bulb, or we have not enough emittivity. So it means that we have L proportional to A square over L. So now we can rewrite it in form of L square must be proportional to A. So this proportion we got from this idea that produced power must be proportional to emitting power, or even equal to emitting power. But from other hand, we know that this power E must be proportional to N. So we have AL proportional to N. And now we can combine these two proportions and insert this A proportional to L squared to this one. So we have L cubed proportional to N, or L proportional to N power 1/3. And now we can use this proportion to find what is proportional to A. So we have A proportional to N power 2/3. So finally, to get a new power NP with the above conditions, we have to create a new filament with these parameters. A prime equal N power 2/3 A, and L prime equal N power 1/3 L. So that's the result. US Physics Olympiad, year 2011, USAPHO, semifinal exam. Problem A4. Solution for this problem you can find below this video in the reference of the description. In this problem we consider a simplified model of the electromagnetic radiation inside a cubical box of side length L. In this model the electric field has a spatial dependence E as a function of x, y, z equal this expression, where one corner of the box lies at the origin of the box is aligned with the x, y, and z axis. Let h be Planck's constant, k be the Boltzmann's constant, and c be the speed of light. Question A. The electric field must be zero everywhere at the sides of the box. What condition does this impose on kx, ky, and kz? Assume that any of these may be negative and include cases where one or more of the ki is 0, even though this causes E to be 0. Solution. Boundary conditions require that for x equal L or y equal L or z equal L, these signs must be equal 0. So it means that argument must be equal to nx pi or ny pi or nz pi, where n, I are integer numbers. It means that we have possible expressions for kx, ky, and kz like this. So that's the solution for question A. Question B. In the model, each permitted value of the triple kx, ky, kz corresponds to a quantum state. These states can be visualized in a state space, which is a notional three-dimensional space with the axes corresponding to kx, ky, and kz. How many states occupy a volume S of the state space if S is large enough that the correspondences of the states can be ignored? So far we can see that kx, ky, and kz could have special values like this one. We can divide our three-dimensional abstract space corresponding to this kx, ky, and kz axes, and this space could be split by unit volumes with a distance pi over L apart. So each state could occupy volume pi over 3 cube in this space, and if we have space volume S, the number of states could be found dividing this volume S by this unit volume. That's N is answer for question B. Question C. Each quantum state in turn may be occupied by photons with the frequency omega equal f over 2 pi equal c multiplied by model k, where c is speed of light and k is length of vector k in this space. If the temperature inside the box is T, no photon may have energy greater than kBt, where kB is Boltzmann constant. What is the shape of the region in state space corresponding to occupied state? Solution. Energy of photon equal this expression, where this h equal Planck constant over 2 pi. So it means that we have this in equation. Energy must be less than kBt. So it means that in our space this inequation corresponds to ball with radius k equal this expression. So that's the shape of our region. Question D. The final approximation assumes that each occupied state contains exactly one photon. What is the total energy of the photons in the box in terms of H, KB, C, and T, and the volume of the box? Again, assume that temperature is high enough that there are a very large number of occupied states. Hint: divide state space into thin regions corresponding to photons of the same energy. Note that while many details of this model are extremely inaccurate, the final result is correct except for a numerical factor. Solution. We already found what is maximum radius of this region. That's k maximum equal this expression. Now we have to do integral in this ball, and that will be triple integral, but we have radial symmetry because energy only depends from the length of this k. So it means that we can split our ball for infinitesimal shells, and the volume for each shell will be ds equal 4 pi k square dk. So we have to do integral. So each state in this region has a photon with the energy this one, and the occupied volume equal this expression. So this shell ds contain total energy equal this one. And the last step, we have to integrate this expression from 0 to k maximum. That will be this expression. After integration, we have this result. And now we can put expression for k maximum, this one. And the final result is this one, where V is volume L cube. This result corresponds to right dependency from temperature in power 4. Only thing that numerical factor is not correct here. US Physics Olympiad, year 2011, USAPHO, semifinal exam. Problem B1. Solution for this problem you can find below this video in the description reference. An AC power line cable transmits electrical power using a sinusoidal waveform with the frequency 60 Hz. The load receives an RMS voltage of 500 kilovolts and requires 1000 megawatt of average power. For this problem, consider only the cable carrying current in one of the two directions and ignore effects due to capacitance or inductance between the cable and with the ground. Question A. Suppose that the load on the power line cable is a residential area that behaves like a pure resistor. 1. What is the RMS current carrying in the cable? 2. The cable has a diameter 3 centimeters, is 500 kilometers long, and is made of aluminum with a resistivity 2.8, 10 power negative 8 ohm by meter. How much power is lost in the wire? Solution. Because the load is resistive, we have a power equal I RMS multiplied by V RMS. And from here we can find what is current RMS. That will be 2000 ampere. So that's the answer for first question. Second question. So first we need to count what is resistance for this power line, which is resistivity multiplied by length and divided by cross-sectional area, which is pi r square. And after putting numbers, we will get 19.8 ohm. And to find what is power loss, we need to use this formula I RMS square multiplied by resistance R, which is 79.2 megawatt. So that's the answer for question 2 in part A. Part B. A local rancher thinks he might be able to extract electrical power from the cable using electromagnetic induction, the wrencher constructs a rectangular loop of length A and width B less than A, consisting of n turns of wire. One edge of the loop is to be placed on the ground. The wire is straight and runs parallel to the ground at height h, much less than the length of the wire. Write the current in the wire as a function of omega and t in form of I0 sine omega t, and assume the return wire is far away. First, determine an expression for the magnitude of the magnetic field at a distance r from the power line cable in terms of I and r and the fundamental constants. 2. Where should the loop be placed and how should it be oriented to maximize the induced EMF in the loop? 3. Assuming the loop is placed in this way, determine an expression for the EMF induced in the loop as a function of time in terms of any of all these parameters and the fundamental constants. 4. Suppose that A equal 5 meters, B equal 2 meters, and H equal 100 meters. How many turns of wire N does the wrencher need to generate an RMS EMF of 120 volts? Solution. For the first question, result is pretty simple. Here we can use regular Ampere law to find what is a magnetic field around the straight infinite wire. Due to radial symmetry, we have this integral equal to pi r b, and after that we can find the well-known expression for magnetic field around this wire. That will be this expression, which is a well-known result. That was the answer for question 1. Question 2. Where should the loop be placed and how should it be oriented to maximize the induced EMF in the loop? A solution for this second question is obvious, because we have this expression for magnetic field, so the total EMF will be larger when we put this loop directly below this wire, and the longest side of this loop must be oriented in the same direction as a wire. So that's the answer. The loop must be in the same plane as a wire, and we need to put it below the wire and as much closer to loop as possible. That's the solution. So first, using Faraday's law, we can find what is EMF in this loop. That will be number of turns multiplied by the change of magnetic flux per unit time. That's a dFB over dt. So we have to find what is magnetic flux for this loop. So magnetic flux will be this integral B by dA, where A is area for small parts of this loop, and due to some kind of symmetry we can represent it in this form. And now we can use this expression for magnetic field and put it in this integral. So result for magnetic flux is this one, but we need to find what is the change of magnetic flux with the time, and in this formula only current is a function of time, and the derivative from current by time equal I0 omega cosine omega t. And now we can put this expression in this formula and find what is EMF. So that will be full expression for EMF in terms of all these parameters in question 3. Question 4. To answer for question 4, we can use this result, but instead of I0 cosine omega t, we can put here I RMS, and instead of EMF RMS. So that will be this EMF RMS expression. Also, we need to convert the omega to a regular frequency. So, using the expression for regular frequency as omega over 2 pi, we have EMF for one turn loop, like this. And that's equal to 0.055 volts. And to get 120 volts, we need to use this number of turns, 7,760. So that was the answer for question 4. Part C. The load at the end of the power cable changes to include a manufacturing plant with a large number of electric motors. While the average power consumed remains the same, it now behaves like a resistor in parallel with a 0.25 Hz inductor. First, does the power lost in the power line cable increase, decrease, or stay the same? You need not calculate the new value explicitly, but you should show some work to define your answer. 2. The power company wishes to make the load behave as it originally did by installing a capacitor in parallel with the load. What should be its capacitance? Answer. Solution. For the first question, if we put the inductor in parallel with a resistor, the total impedance will decrease as using Ohm law. Now we can use voltage, current, and impedance as complex numbers. And in this case, we have Z, this expression. It means that now absolute value for Z is less than R. It means that Z decrease, I increase, current will increase. That's the answer for question 1. Question 2. The power company wishes to make the load behave as it originally did by installing a capacitor in parallel with the load. What should be its capacitance? Answer. To compensate the influence of this inductor, we need to put in parallel capacitors to cancel a complex part of this impedance. That will be this expression. From here we can find that capacitance must be equal to this expression, or in terms of numbers, that will be 28.1 microfarad. So that's the final answer for problem B1. US Physics Olympiad, year 2011, USAPHO. Semifinal exam. Problem B2. Solution for this problem you can find below this video in the reference of the description. A particle is constrained to move on the inner surface of a frictionless parabolic ball whose cross-section has equation z equal kr square. particle begins at height z0 above the bottom of the ball with a horizontal velocity v0 along the surface of the ball. The acceleration due to gravity is g. Question A. For a particular value of horizontal velocity v0, which we will name vh, the particle moves in a horizontal circle. What is vh in terms of g, z0, and or k? Solution. Suppose that a particle moving on a distance r from axis z and on height z. In that case, we can write equations for motion. On this height, we have normal force, and we have slope of this curve with angle theta. So we can write equations for this motion. In vertical, we have this equation that mg must be equalized by normal force multiplied by cosine theta. In horizontal, we have normal force multiplied by sine theta, create a centripetal force to move by circle, which is this equation. We have mv square over r equal normal force multiplied by sine theta. Now we can divide this equation by this equation, and we have tangent theta equal this expression v square over gr. But from other hand, we can find this tangent by taking first derivative from z by r. That will be tangent theta equal 2kr. And now we can equalize these two tangents, and we get v square equal 2gk r square. But kr square, that's z0. So we have v square equal 2g z0. And this is our answer for velocity vh. That will be vh equal square root from 2g z0. That's the answer for question A. Question B. Suppose that the initial horizontal velocity is now v0 greater than vh. What is the maximum height reached by the particle in terms of v0, z0, g, and or k? Solution. In this part, we can use energy conservation and angular momentum conservation, because there are no forces which can change the angular momentum. So first, let's write equation for energy conservation. In point height z0, we have mg z0 plus 1/2 mv0 square equal same thing in point z. So potential energy in point z, which is mgz, plus kinetic energy in point z, which is 1/2 mv square. From other point, we have angular momentum conservation. In lowest and highest points, we have velocity has only horizontal part, no vertical part. And in the lowest point, we have mv0 multiplied by r, which is square root from z0 over k. That's equal to mvr in the highest point. Now we can cancel masses in both equations. We can square a second equation, and we will get next equations. This is energy conservation, and this is angular momentum conservation. So now we can rewrite it in form of this one, and we can express v square from this equation. So in the highest point, v square equal z0 over z multiplied by v0 square. And we can put this expression to this equation. That will give us a quadratic equation to z. And the solution for this equation we can write here. That will be this equation. If we can see carefully, this is square root from this expression. That's exactly square root from perfect square, which is a v0 square minus 2g0 square. And we can write two roots for this solution. That will be z1 is z0, which is trivial, and the other z2 equal v0 square over 2g. And because v0 greater than vh, so we have z2 greater than z0. That's the solution for question B. Question C. Suppose that the particle now begins at height z0 above the bottom of the ball with the initial velocity v0 equal 0. First question. Assuming that z0 is small enough so that the motion can be approximated as a simple harmonic, find the period of the motion in terms any or all of the masses of the particle m, g, z0 and or k. Solution. Because z0 is very small, we can assume that angles are very small. So correct assumption for this motion will be that angle theta approximately equals sine theta, approximately equal tangent theta, and tangent theta equal dz over dr, which is 2kr, and cosine theta approximately equal 1. Now let's write equation for tangential acceleration. Tangential acceleration we can find from this formula. Also we have centripetal acceleration, but because motion is very small, we can neglect centripetal acceleration. And tangential acceleration we can convert to radial acceleration. And for radial acceleration we have this equation. It's equal tangential acceleration multiplied by cosine theta, which is negative g sine theta cosine theta. And because angles are very small, cosine is about 1, sine theta is about theta, and finally we will get negative g theta, but theta equal 2kr. So we have equation AR equal negative 2kgr, which is corresponding to oscillation with omega equal square roots from 2kg. And from here we can find what is the period. Period will be 2 pi over square roots from 2kg. So that's the answer for part C, question 1. Part C, question 2. Assuming that z0 is not small, will the actual period of motion be greater than, less than, or equal to your simple harmonic approximation above? You need not calculate the new value explicitly, but you should show some work to define your answer. Solution. We already found that radial acceleration equal tangential acceleration multiplied by cosine theta, which is equal to negative g sine theta cosine theta. But we found that only in case of AR equal negative g tangent theta, which is equal to negative 2kgr, we have a perfect simple harmonic motion. But in our case, we always have sine theta cosine theta less than tangent theta. It means that in any point radial acceleration less than acceleration for simple harmonic motion. It means that period will be greater than for simple harmonic motion. That's the solution.